Okay, let's get started. Thanks for attending today and not starting your spring recess early. Good to see you all. Last class before we have a little bit of a break. Where are we and where are we going? Undergraduates, you are now tackling assignment 8, which is not due this coming Monday, the following Monday, the 18th. It's good timing because assignment 8 is a little bit longer than the other assignments. In this case, you're finally going to be discarding this minimal scissor bot that you've been using so far and replacing it with the quadruped that you've seen before. Throughout assignment 8, you're going to be using this engineering drawing. You can either draw it yourself from scratch, you can print it out and annotate it. You're going to be obviously adding a large number of objects and joints and sensors and motors and sensor neurons and motor neurons and synapses. In my experience, it's good to have just a single piece of paper and annotating everything on there as you add these pieces. As you'll remember from the first few assignments, always a good idea to just add one piece at a time. Run, debug, compile, make sure the object is where you expect it to be, the size you expect it to be, the orientation you expect it to be, and so on, right? There's always a temptation to add a whole bunch of stuff, compile and hope for the best. Take your time, cycle through this. You've got 2 weeks to get through assignment 8. Off you go. Let's see, I think that's all I had to say about assignment 8. And graduate students, you are carrying on with your third weekly report, which again will be due in 2 weeks' time. Sound good? Any questions about the assignments, final project? We're all good? Okay, so back to the open challenges in evolutionary robotics. It's a young field. There's a lot of big problems out there that no one has a good answer to. You may be the person to finally come up with the answer to some of these open challenges. We started last time by talking about modularity. If you look at biological systems are modular at all levels of organization. The ultimate module, the cell, is sort of the building block of all organisms on Earth. If you think about genetics itself is modular. Luckily, if mutation changes the eye color in a human infant, it doesn't change all other aspects of the physiology of the human infant, right? So mutations to biological DNA has local impact on phenotype. Remember that phenotype is the umbrella term for behavior and physiology, right? So one local change to the genotype usually has one local change to the phenotype. That's another kind of modularity, right? Unfortunately, that usually if you apply an evolutionary algorithm to a robotics experiment, gradually evolution will make the robot less and less modular over time. So we need to change the way we go about evolving neural networks inside of robots to help evolution or bias evolution towards modular solutions rather than non-modular solutions. Why do you think the standard evolutionary algorithms that we've sort of seen in this class so far tend to create non-modular solutions? Any ideas?
Did we randomly pick the gene to modify?
We randomly select the gene, so most of the time the gene corresponds to one synaptic weight in a neural network. You change that synaptic weight, which influences how sensor values flow through that synapse to one or a few motors. The motors move, the robot moves. That causes a sensory repercussion. That's the embodied part. And often when one motor of the robot changes at the next time step, many or all of the sensor values change. So that feedback loop through the environment tends to mean that even a local change to a synaptic weight tends to have a global impact. It's very hard for evolution to sort of modularize or localize phenotypic impact of mutations. It's a big topic. We're just looking at one potential solution to this problem today. Okay, so the problem is lack of modularity, really. And the solution is to try and get evolution to find modular solutions. And we talked last time about why modularity is useful. It's useful not just in biology and in robotics. Hopefully in computer science, you're getting better and better at writing modular code. Modular code is good news for you because as you continue working on your code, you can tinker with one module of the code without disrupting the function of all the rest of your code, right? Modularity is usually a good thing across the board in lots of different domains. Okay. It's hard to impose modularity on our robotics experiments because, as usual, thinking about thinking is misleading. We might look at the task that we want our robot to perform and say, obviously, we can break this task down into these 2 or 3 or 10 subtasks and evolve different subnetworks for these different tasks. It's obvious how the task should be partitioned into modules, but often what we see from outside or from far, from a distal perspective, is often not an appropriate way for the robot to break its task down into subtasks. Okay, so what we would prefer to do instead is allow evolution to try and discover subtasks on its own, and we're going to look at an attempt to do so using the little Kepler robot down here, which, as you'll recall from last time, is going to drive around inside this arena and try and pick up these 5 wooden cylinders, pick them up, take them to the edge of the arena, and drop them outside the arena. Just as a reminder, our little Kepler here has 6 infrared sensors, which are basically distance sensors, and it's got a 7th light barrier sensor between the 2 pincers of its gripper. So it can tell whether there's an object between, whether it's holding an object or not. And we've got 4 motor neurons which spin. The first one spins the left motor, second one spins the right motor. The third one triggers this behavior, and the 4th motor neuron, if it fires, triggers this behavior. Okay, so we ended last time by thinking about this problem, and here's one possible way you could think about partitioning the task. And as I've already set this up, as you can probably imagine, this is not appropriate for the robot, as we'll see in a moment. You can probably imagine other ways of partitioning this task. How are we going to approach this? One of the reasons why I like this paper that we're drawing the material for today's lecture from is that they go about this in an interesting way. They're going to evolve the same robot on the same task with the same fitness function and the same evolutionary algorithm. But in this case, they're going to do a whole bunch of evolutionary runs. They're going to do a bunch using this neural network, then start again and do a bunch of evolutionary runs with this neural network, then this one, and a 5th one, which we'll talk about in a moment. As you can see just visually, these 4 neural networks increase in complexity. The first one is about the simplest thing you can imagine. We have our 7 sensors down here, and we connect each sensor to each of the 4 motor neurons that trigger these 4 behaviors with a synapse. Pretty straightforward, right? Next neural network, same thing, 7 sensors, 4 motors, but we're going to introduce 4 hidden neurons. What do hidden neurons buy us, or what do they buy the robot? What are hidden neurons useful for? To map a nonlinear function, right? You remember when we saw the XOR function? That's a nonlinear Boolean function. There was no combination of synaptic weights in a feed-forward network that would solve the XOR problem. The robot here probably doesn't need to solve the XOR function, but if there is a nonlinear transformation from sensor values to motor neurons that are necessary to solve this task, then we should be able to evolve robots using this neural network that solved the problem, but we should fail to evolve robots using this neural network to solve the problem, right? Okay. This one here, we have our 4 hidden neurons as before, but it's drawn in an odd way here. You'll notice that there are synapses that are going from these 2 hidden neurons around to these 2 hidden neurons, which is just a different way of drawing a recurrent layer. So now we have recurrent synapses in our hidden layer as well. What do recurrent connections buy us?
Memory.
Memory, right? Is memory required for this task? Does it need to remember anything? I see a lot of people shaking their heads. Doesn't seem like it, right? Thinking about thinking is misleading. Maybe it's helpful, maybe it's not. We'll know, because if robots evolved with this neural network do better than robots evolved with this neural network, then memory was useful in this task.
Right? Considered memory to know that you picked up a block and are carrying one?
It's not clear, right? Memory of what? That's sort of up to evolution to decide what it may remember, assuming again that memory is useful. Okay, neural network D is the investigator's attempt to impose modularity on this task. Let's assume, again from a distal point of view, that we can break this task into two subtasks. Task 1 is what to do if you're not holding a block, and task 2 is what should you do when you are holding a block. Presumably, the robot should do different things in those two different conditions. So let's create two separate networks. The first network is going to control the motors when the gripper is not holding a block. But the moment that that light barrier sensor is broken, the moment that there's a block between the left and the right pincer of the gripper, then this neural network will be released from the motors, and this subnetwork will grab the motors and control it. You'll notice that there are synapses going from all 7 sensors to these 4 neurons, and synapses going from all of these 7 sensor neurons to these second set of 4 motor neurons. Where have you heard this idea before of parts of the network grabbing the motors and then releasing them again, depending on what the sensors sense?
With the fast and slow functions.
Not quite. In the fast and slow neuron connection with the little humanoid, it was always the fast neurons that were controlling the motors.
The mode switching, but I can't remember the...
It's like mode switching.
What was the one where they had, like the Roomba that said, the first time in seek mode or...
Exactly. So the subsumption architecture, which we introduced way back at the beginning of the course, this was actually proposed by Rod Brooks at MIT back in the 1980s, with the idea that different parts of the network would control the motors depending on what's going on. And if there's ever a more urgent situation than cleaning the floor, like, for example, you're about to topple off the top of the steps because a sensor pointing down on the underside of the Roomba suddenly detects distance, then suddenly a different network should take hold of the Roomba, which is to turn the Roomba away from the top of the stairs. So who knows what's inside the Roomba, but it's probably some version of the subsumption architecture. Right? Again, however, in the Roomba, and in this case, the investigators or the roboticists are making an assumption about what these different situations should be. Right? Imagine a mutation that hits one of the synapses in here. Tell me about how that would alter the behavior of a robot controlled by this neural network. If there's a mutation that alters one of the synapses going from the sensors to this first motor subnetwork, how would it alter the behavior of the robot?
It might just alter the behavior in relation to one of the tasks that it's trained to perform, such as like picking up a block or moving a block to the edge.
Exactly. By definition, it's only going to affect the behavior of the robot in one of these two conditions. And the first condition is the robot doesn't have a block, right? So what the robot does when it's not holding a block is going to be impacted by a mutation here. But what the robot does when it is holding a block is unaffected. Right? So we've already built in this nice property of modularity now that mutations only affect local phenotype. In this case, it's local in time, maybe not in space, or local in terms of the condition. However, maybe we partitioned this task incorrectly. Maybe this is not a good way to break this task into digestible pieces for the robot. So the fifth and final network here is designed to allow evolution to do two things. First of all, come up with different ways of carving up the task into different subtasks, and evolve the synaptic weights to dictate what the robot does in those different subtasks. All right, let's have a look at how neural network E works. Same as before, we have our 7 sensor neurons down here, and you'll notice we have 4 groupings of 4 output neurons at the top. Each one of these 4 groupings corresponds to one of these 4 behaviors: spin the left wheel, spin the right wheel, pick up, or release. Okay. Within any one of this grouping, you'll notice there's 2 black neurons and 2 white neurons. Black neurons are what selector neurons, and the white neurons are output neurons. What are selector neurons? Well, mentally simulate the robot driving around in the arena with this neural network. As it's driving around, the 7 values at the input layer here are changing, and they are flowing up from the sensor layer to the motor layer. And imagine the values arriving at these 2 selector neurons. These are floating point values between -1 and +1. And one of these 2 values is going to be larger or more positive than the other one. Let's assume that the left selector neuron is greater than the right selector neuron in this grouping. That's the neural network signaling that the left output neuron's value should be sent to the left motor. So it's like a gating or selection mechanism. It dictates which of the 2 values at these 2 alternate output neurons are able to control the left motor at any given time. Make sense? Same thing for the right motor. We have a pair of selector neurons. If the left selector neuron value is more positive than the right selector neuron value, then the left output neuron controls the right motor, and so on. So far, so good? So we've got the same idea in E as we had in D, which is that different output neurons can grab or send their value on to their respective behavior. And which output neurons are grabbing on to these 4 basic behaviors is being dictated by the selector neuron. Okay. Now, what these output neuron values actually do, it's not exactly clear here. Let's think about these 4 groupings at the moment. In each of these 4 groupings, it can either be the left or the right output neuron that grabs the motor at any given time. So how many discrete states are possible in this network? What would be a state in this case? We don't have binary values or integers, so it's hard to think about discrete states because all 16 of these output neurons, they're all floating point values, but there are discrete situations that can occur here. What are those discrete situations? Todd?
Whether the left or the right is a binary, so it's like greater than or less than, so there's 4 binary choices.
Exactly, there's 4 binary choices. So if we think about which of these 2 neurons is greater than the other, there's a binary situation which is going to switch whether the left or the right motor neuron in that grouping has control of the motors at any given time. So we've got a binary state here. Either the left output neuron is in control or the right output neuron is in control. Same thing here, same thing here, same thing here. How many discrete states are possible? 16, right? So there's 2 possibilities here, times 2 possibilities here. 4 times 2 possibilities here is 8, times 2 possibilities here is 16. We've got 16 states, and you can think of those as different modules, if you like. Actually, let's keep them separate. Let's think of these as states, and we have, in essence, 8 different modules. Whether this module is in control, or this neural module is in control, or this neural module is in control, or this one, and so on. Make sense? Imagine we evolve a neural network E for a couple hundred generations on the robot. We get a successful robot that cleans the arena, but there is no switching of states in the best neural network. So for example, all left output neurons are always controlling the motors, and the selector neurons never switch. It's always the left-hand ones that control the behavior of the robot while it cleans the entire arena. Is evolution making use of modularity in this case? No, it's just basically it's one neural network. It's the four left output subnetworks. Imagine the robot drives around and all of the four left-hand output neurons are in control. Suddenly the robot grasps an object, and one of the four groupings among its pair of selector neurons switch values, and suddenly the right-hand output neuron in one of those four groupings takes control at exactly the moment that the robot grasped the object. Now we have a modular network, right? Evolution is saying, I have two modules, all four output neurons. That's module 1. Module 2 is three output neurons and three left output neurons and one right output neuron. That's module 2 that I'm going to use when I'm grasping an object, right? That would be the simplest thing. And as usual, evolution is going to come up with something that's not that simple. But at least we can see in in neural network E, we're giving evolution the option about whether to use modularity at all. And if it chooses to use modularity, it can sort of sculpt how that modularity works, when that modularity kicks in. And of course, because evolution is tuning the weights of the synapses from the input neurons to the output neurons, it's also, as usual, determining what the robot should do in those different configurations. So far, so good? Okay. You're all experts on evolutionary robotics at the moment. Which of these 5 neural networks did better than others? It's betting time again. You can be sure of one thing. This paper was published, so neural network E probably did okay. No other guesses? All right. Okay, so let's have a look at our fitness curves again. And let's, before we look at these fitness curves, let's talk a little bit about how evolution was done. We're going to evolve, we're going to do a set of evolutionary runs with each of these. We're going to do 10 evolutionary runs for each of these 5 neural network controllers. So we've got a total of 50 evolutionary runs in total. For each controller in each population, at each generation, in each run, we're going to evaluate that neural network 15 times. We're going to put the robot at a random position and orientation inside the arena, drop in the neural network, and allow the robot to move for 2,000 actions or 2,000 time steps, if you like. All of this work was done in simulation for the moment, so 200 time steps. Or if the robot had grasped during one of these epochs, if the robot grasped an object, got it to the edge of the arena, and successfully dropped it outside the arena in less than 200 time steps, that epoch ended. The robot was put back to another random location and orientation. The arena state was left the same, and the robot was allowed to do its thing again. And at the end of 15 epochs, fitness was basically how many blocks you got outside of the arena. Okay. All right, as you can see, obviously A did pretty poorly, and all 4, at least by 1,000 generations, all 4 neural networks were doing pretty well. So the fact that A was doing worse than B, C, D, and E, what does that tell you about this task at least? Yep.
It's a nonlinear.
It requires a nonlinear transformation from sensors to motors, that's for sure. So you at least need a hidden layer at the minimum. Yes?
B B, C, and D do not have a hidden layer, so that's...
They do have a hidden layer. It's just drawn differently in this case. So if you look at C here, you'll see that the 7 neurons down here, they're all connected directly to the motors, to the 4 motors up here, but they are also connected to these 2 hidden neurons here. These 2 hidden neurons are connected to these 2 hidden neurons, and these 2 hidden neurons are connected to these 2 hidden neurons and the 4 motor neurons. Just a different way of drawing a hidden layer. They all, B, C, D, and E, B, C, and B and C have hidden neurons, but D and E do not. Kind of interesting. All right, so it's a little more complicated than just requiring a nonlinear transformation. You need either a hidden layer or some form of modularity. From this fitness curve plot at the top left, what else can you tell me about the relative performance of these neural networks? And what does that tell you about this task? Nathan.
C didn't do as good, so it probably doesn't need memory.
It probably doesn't need memory here. Yeah, it doesn't really buy much compared to B. For once, thinking about thinking was not misleading.
He also became became better quicker.
Exactly. So the evolution was able to evolve the E networks faster than the other neural networks. What this means is that the E networks were more evolvable than the other ones. There's a concept in evolutionary biology which we're just going to touch on from time to time in this course, which is evolvability. The basic idea there is how easy or difficult is it for evolution to find mutations that improve the fitness of a biological population, or in our case, a population of robots. So we can see that choosing these different neural networks make the system more or less evolvable. So the E networks are definitely more evolvable than the other 4. What does that tell us? In particular, E did better than D. What does that tell us?
More complex is no way better.
More complex is not always better. Maybe. E is still pretty complex.
It looks like E was built for evolution to kind of decide the modularity versus in D, the investigators tried to define modularity themselves.
Exactly. So in D, that particular choice of modularity, which seems obvious to us, do behavior A when you're not holding a cube or holding a cylinder, do behavior B when you are, but you figure out what behavior A and B is. That modularization of the task, which seems obvious to us, is not appropriate for this robot under these conditions, right? So thinking about thinking is misleading. However, since E did do so well, that means there is modularity in this task that's useful, and clearly evolution was able to find it. Okay, you should all be dying with curiosity to know what that modularity is, right? Okay, we'll look at that in a moment. Before we do, let's just do a little bit more analysis. Another nice thing about this experiment, it's one of the few evolutionary robotics experiments where they did transfer neural networks from the simulated robot to the physical robot. So they transferred the controllers onto the physical Kepler robot here, put it in an actual arena with little wooden pegs, and with no modification to the neural networks. Most of A through D networks failed miserably, but the E networks transferred pretty well. So pretty interesting that evolution was able to find some modularity, and that also transferred to reality in this case. So in this picture here, they're showing how many among a set of evolved E networks, in this case, that successfully cleaned the arena in simulation also did so in reality, and it's 7 out of 10 or 8 out of 10 of those controllers did so.
Did they make an attempt classify why E was more portable, more?
They did
yeah,
not. They did not. It'd be an interesting thing to know. They didn't talk about that too much. Kind of interesting. Okay. All right, so take a deep breath, and we're going to try and figure out what evolution did in just one evolved E network. So they took the best E network. Remember that there are a total of 16 possible states, right? As the robot's driving around cleaning the arena, the left or the right output neuron can take control of its respected motor primitive. These 4 simple behaviors here at any time. In the best evolved network, there were only two states. So in the case of the right motor neuron, there are cases in which the selector neuron pair changed relative values and switched which of the 2 output neurons was in control of the right motor. For the other 3 cases, there was always one or the other output neuron that was in charge. There was no switching that happened in those 3 groupings. So they're basically 2 modules, which is good news for us. We only have to try and figure out what these 2 modules are and what they correspond to. All right, let's see if we can figure this out. Let's have a look at the behavior of the robot itself first. So obviously the line here corresponds to the trajectory of the robot. And if we find this point here, this is where the robot started in one epoch. It drove around. It's a little hard to follow this here. And at some point came into contact with one of these pegs, picked it up, and carried it to the edge of the arena and dropped it out. And as you can see in this case, at the next epoch, it was dropped at another initial position and orientation, drove around, found a second peg, picked it up, took it somewhere, and dropped it outside the arena. Did that for a third and never found the 4th or the 5th peg. So it did pretty well, but not great. All right, that's what the robot did. We're now going to look on the horizontal axis here of the timeline for this particular behavior. So now we're looking not at evolutionary time, but just the time that it took for this single robot with this single neural network to get rid of these 3 pegs. Let's start with the top panel here. So mod is which module controlled the right motor at a given time. So blank regions indicate that the left output neuron was in control of the right motor at that time, and a black stitch or a black line here represents that there was a switch and the right output neuron was in control of the right motor at that time. So far, so good? All right, we know we're already in trouble because there aren't big black contiguous black rectangles followed by white rectangles. If there were, we would know that for that given period of time, that module was in control, was continuously in control, and then something happened and the other module took control of the right motor. The switching between the modules goes back and forth very quickly, which at least for me is already non-intuitive. It's not really how we think about modularity, at least when it comes to robots and organisms, right? I'm in lecture mode right now for the next 55 minutes. When I get back to my office, I will switch to email mode for, unfortunately, a long period of time, and then switch to another task, and so on. You can be modular, and no one said you have to stick with a given module or a particular behavior for a long contiguous period of time. We do. That's what feels natural if we think about modular behavior. Not so in the case of our simple Kepler robot here. All right, let's push on. Let's see if we can find a correspondence between when one or the other module is in control and what was going on in the life of the robot at exactly that point in time. Okay, so WT here corresponds to wall or target. So an upper bar represents the robot is seeing the wall. Remember, it has these 6 infrared sensors, which are distance sensors. So if one or more of those distance sensors is hitting a wall, the robot sees the wall. Whether it does anything with that information or not, we don't know. It sees the wall for a little while, sees the wall for a little while, and then sees the target, moves around. At this point in time, it sees neither a wall nor target. Then it sees the same or a different target, sees nothing, sees the wall for a long period of time, then nothing, and so on. Do these two modules correspond to when the robot sees the wall or the target? Not really. If you did, you would expect to see whenever there's black up here, there's an upper bar here, and whenever there's white here, you would see a lower bar here, or none. Whatever it is, again, intuitively, you might think that different behaviors are in control depending on whether the robot sees the wall or the target. So the first guess that the investigators made, at least in that case, that's not what the robot is doing in this case. Okay, how about these 4 simple motor primitives? So left motor spinning. Most of the time the left motor is spinning. You can see it slows and stops periodically during this period. Here's the right motor spinning and then slowing and stopping periodically in here. Pickup behavior, we can see that the pickup behavior was triggered once, twice, 3, 4, 5, a little bit again, a little bit again. And then finally, the release behavior is triggered most of the time the robot is released. In this period, released is inhibited, which means it's doing the opposite. So these are the 4 basic behaviors. Do they correspond to one of these modules or the other? Nathan.
Looks like there seems to be a bar corresponding with the beginning of a release block and the end.
The beginning of a release block, like here, corresponds with fast switching between module A and module B. A little bit of a correspondence there. Yeah, maybe a little bit of a pattern there. So there's maybe a bit of correlation here, but again, it's not too obvious that there is a correlation. Let's keep going. Here's the firing of the 6 infrared sensors. Any correlation there? Some kind of.
L2 and L3 aligned with when the left and right motors slow down, so it might detect an obstacle and decide to stop.
Maybe you can start to get a feel for kind of what the robot is doing from its point of view. 2 and 3 are firing. You can see that the 2 motors slow down a little bit. So that makes sense. 2 and 3 are kind of front left of the robot. So that sort of makes sense. Do these blocks of behavior correspond with module A or module B? Kind of have to squint at this one. Not quite. A little bit of overlap. Hard to say. Let's keep going. The 7th sensor, the light barrier sensor, you can see that the light barrier sensor was triggered during these 3 periods of time. What do these 3 periods of time represent? What's happening to the robot during these times?
Each time it's successful.
Exactly. So we can see pretty clearly at least when the robot is holding the block. Does the periods during which the robot is holding the block correspond to the 2 modules, one or the other of the 2 modules? I think you kind of get where this is going, right? Not quite. It would be nice if that were the case. There's a little bit of more white here when this is black and vice versa, but also that kind of falls apart as well. So it's not partitioning the usage of these 2 modules depending on whether it's holding the block or not. These investigators were very brave. They just carried on and they came up with 1, 2, 3, 4, 5, 6, 7, 8 subtasks or 8 situations that the robot experiences during its lifetime. Maybe those situations correspond to module A or module B. Situation A, it's carrying the object, which you can see, obviously that corresponds to these times here, and hopefully it's looking for a wall during these periods. B is when the gripper is empty. C are periods when it sees anything, target or wall. D doesn't see anything. E, it's moving towards an object. F, it's approaching the wall, avoiding an object, avoiding a wall, and so on. Is there any correspondence between A through H and mod?
Each is a pretty good indicator.
H is not too bad, right? So good thing that they stuck it out. At some point, avoiding a wall seemed to dictate which of the two modules was in control. It's again not perfect, but okay. So what does that mean? It's not avoiding a wall and it uses module A. It is avoiding a wall, it's using module B. I don't know, at this point I've lost the plot here. It's a little bit difficult to understand what sub-behaviors these modules correspond to. Okay, so maybe in retrospect at this point in the course you're not surprised. Evolution comes up with a useful solution here. It's very difficult for us to intuit exactly what evolution has found. I think we're going to skip over this one. It's just more analysis of the robot. This one's a little more interesting. We're going to take the best, one of the evolved E controllers. This is the best one ever. It never makes mistakes. So like we've seen a couple times before now, they're going to play back the E controller in the robot under lots of different conditions, many, many more conditions than E ever saw during evolution. And we want to see whether the E controller enables the robot to do the right thing during conditions it's never seen before. What are those additional conditions? I will zoom in here. They broke these initial conditions into 4 categories. The robot is facing the wall, but its gripper is empty. The robot is facing the wall, but the gripper is full. The robot is facing a cylinder, but its gripper is empty. And the robot is facing a cylinder, and its gripper is full. And then in each of those conditions, they put, let's try this one. This is the robot the robot is near the wall, not necessarily facing the wall. So near the wall or near a cylinder. They put the robot near the wall, and then they altered the orientation of the robot toward the wall. So 0 meant the robot was facing the wall head on, and 180 meant the robot's near the wall, but it's facing away from the wall. So they tried all 360 orientations, 5 millimeters away from the wall, 10 millimeters away from the wall, 15 millimeters away from the wall, and so on. So lots of different conditions where it's near the wall, but it's oriented differently. And in all these cases, the gripper is empty. What should the robot do in all those conditions?
Turn away and go look for something.
Turn away and go look for something. So white pixels represent that neither the pickup behavior nor the drop behavior was triggered, which makes sense. At this point, it should just drive around, go find a peg, right? Same neural network, but now under different conditions. The robot is still placed near a wall at different orientations and a slight distance away from the wall, but now it's holding a peg. Gray pixels represent trigger of the release behavior. And as I mentioned already, this neural network is not making mistakes. You can see that if it's too far away from the wall, it doesn't drop the peg, which is good. And when it's facing away from the wall, it does not drop the peg, so that's good news. It only drops the peg when it's near the wall and facing the wall. Near enough that if it drops the peg drops on the far side of the wall. So the robot is doing the right thing. You'll notice there's a little white triangle in the middle here. We'll come back to that. That's the situation where the robot is right up against the wall, facing the wall, holding the cylinder, doesn't release it. Okay. Here's the inverse situation. So now the robot is near a cylinder and its gripper is empty. What does the robot do in these conditions? It picks it up, but only when it's facing the cylinder and very close to the cylinder. Makes sense, right? The robot is holding a cylinder, and it goes near another cylinder, does the right thing, right? It does not drop the cylinder it's holding and does not try and pick up the other cylinder. Perfect. Okay. Here is a second E network. This one mostly does the right thing but makes a few mistakes. Where are the mistakes?
When the gripper is full, it tries to pick up another one.
Exactly. When the gripper is full and there's another cylinder nearby, there's a small amount of gray here, and gray is the release behavior. So it drops the cylinder in that case, right? So this small triangle, small gray triangle down here is a mistake. Remember that this is a situation the robot has not experienced during evolution. So I want you to pay attention to this part of the slide, and I'm going to alternate between this slide and this slide. On this slide, black pixels represent situations that the E controller experienced during evolution, and white pixels correspond to situations this E controller never experienced during evolution.
Sorry, what's the y-axis in these plots?
The y-axis is how far the robot is away from either the wall or the cylinder. All right, so points down here at 0, 0. This x equals 0 means the robot is facing either the wall or the cylinder, and a y of 0 means the robot is right up against the wall or right up against the cylinder. Okay? All right, so let me alternate back and forth. Why does the robot make a mistake in this case?
It's never encountered that scenario.
It never experienced that scenario during the evolutionary process, right? So at the end of this experiment now, we can conclude a number of things. The first thing is that the evolved neural network is in control of what experiences the robot has during motion, right? All the different possible experiences don't happen. The robot drives around in a particular pattern, so these white pixels correspond to experiences it never had. Evolution can also decide whether the overall behavior, which is cleanup arena, whether that overall behavior should be broken down into modules by evolving the usage of the selector neurons, the black neurons, the switching neurons. And if it does create different modules by changing the values of the selector neurons, it can decide which situations should trigger switching of modules. It does that by evolving the weights that go from the sensors to the black neurons, right? So evolution is saying under these particular sensory states, or for these particular sensory values, I want to use this module, and for these other sensory values, I want to use this other module. Finally, if evolution has created these different modules and tuned the conditions under which these modules control the behavior of the robot, it can finally evolve the synapses connecting the inputs to the white output neurons, which dictate what the robot does when these different modules have control of the motors. Okay. A relatively simple neural network, relatively simple robot, simple task, but it's quite a challenge for evolution, right? I like this experiment also because this is one of the few experiments where the investigators really try and step back from the design process. Thinking about thinking is misleading. We don't want to tell evolution to be modular. We don't want to tell it which modules to use. We don't want to tell it what to do with these different modules. Evolution sort of figures everything out here on its own. Okay. So one good approach to imposing modularity, there's a lot more work on this subject. We just sort of scratched the surface today. Any questions about that before we move on? Yes,
If you were
Everest.
to design a robot that you want to be modular, could you evolve a different modular structures on their own, or would that be pretty difficult because it's a fairly steep hill in the landscape?
You mean other than saying there's two different modules that control each of
Exactly,
them?
yeah.
Exactly. It gets much more difficult here. The overall architecture of this neural network is fixed, right? We have these 4 different basic behaviors. We've assigned 4 neurons to them. We've decided there's no hidden neurons, no recurrent connections. We've made a lot of architectural choices. Could we take yet one step further back and say, evolution, you figure it out? The evolution of neural network topology or architecture is already a challenging task, and perfect timing, that's what we're going to tackle in lecture 14, starting now, unless there's any other questions. No? Okay, so again, a big challenge in the field is not just evolving synaptic weights for a fixed architecture neural network, but allowing evolution to design the architecture itself. This is a pretty tricky thing to do. So these 2 cryptic acronyms down here, NEAT and HyperNEAT, these are not actually problems. These are solutions to a problem, which is how do we evolve neural network architecture? Let's have a look at that. Okay, so we'll start with the problem. This problem is usually referred to in the literature as the competing conventions problem. And what is the competing conventions problem? Well, if we want to evolve the architecture of a neural network, you can imagine now we have a population of neural networks, and each one neural network in the population might have a different architecture. Some may have more or less hidden neurons. Some may have more or less recurrent connections. Some may have more or less layers of hidden neurons between the input and output layer. How can we possibly evolve all of these different creatures? One of the things that we would like to do is to be able to cut different neural networks in pieces and glue those pieces together to create yet new neural networks, which is introducing the idea of crossover. Everything we've seen up till now has been just using mutation. We're just taking one synaptic weight in a fixed neural network architecture and changing that synaptic weight a little bit. But we'd like to be a little bit more ambitious. We'd like evolution to be able to add and remove neurons and synapses, take different parts of different neural networks, glue them together, which in theory you can write an algorithm that does that. If you do, and you can try this with your existing code base, you will quickly see that most alterations you make to a neural network, other than just tuning the weight of one synapse, will usually break the new neural networks. Here's 2 neural networks here, a Mac and a PC. We're going to cut the Mac in half and we're going to cut the PC in half and glue the 2 halves of those 2 computers together. What do you think this Mac PC hybrid is going to do when you try and turn it on? Absolutely nothing, right? It doesn't work because if you look inside a Mac and a PC, they have very different internal architectures. They have competing conventions. You can't just blindly cut things in half and glue them together. You can't cut one car in half and another car in half and glue the 2 parts together. You're all laughing because it seems so ridiculous. Go have a look at the neural network literature. There's been attempts for decades to do exactly that, and surprise, surprise, like laptops and cars, it also doesn't work very well with neural networks. The good news with at least simple neural networks is we can really look at why and try and come up with a way to solve this competing conventions problem. Okay, so here's my little cartoon example here. If you remember back to our discussion about the XOR function, we were able to create a neural network that solved the XOR function by having 2 hidden neurons, and those hidden neurons computed 2 subfunctions. One was responsible for computing and the other one was responsible for computing or, and then we combined those 2 subfunctions at the single output neuron, which successfully computed the XOR function. So one way of thinking about neural networks is that each hidden neuron inside the hidden layer evolves to perform some subfunction, and evolution then tunes the weights that are going from the input layer to the output layer to figure out how to combine these subtasks or these subfunctions into the correct overall function. Forget about and or now. Let's just replace them with subfunction A, B, and C. Let's imagine in the population we have these two neural networks. As you can see, they have the identical architecture. They all have 3 hidden neurons, same number of synapses. But unbeknownst to, and all 3 of them successfully compute these 3 functions, these 3 subfunctions. But they compute these 3 subfunctions using different hidden neurons. Right? So again, your Mac and your PC, under the hood, both types of computers do sort of the same thing. There's a CPU somewhere and a hard drive somewhere, a memory unit somewhere, but they're in different positions and sort of wired up in slightly different ways. Let's imagine further that both of these neural networks compute A, B, and C, maybe not perfectly. They're getting close, but not quite. So evolution wants to carry on. Let's imagine that this network does A and B perfectly, but is having a little bit of problems computing C correctly. This neural network computes C perfectly, but is having a little bit of problems with A and B. Wouldn't it be lovely if we could cut these 2 neural networks in such a way that we cut out the perfect A and the perfect B, get rid of the imperfect C, and combine that perfect A and B from parent 1 with the perfect C from parent 2. If we could, we'd produce one child network that had A, B, and C in it, and computed all 3 of those subfunctions perfectly, and did better than either parent, right? This is the dream of all parents, right? That the child jettisons all the bad stuff from the parents and combines together the good stuff, the complementary good stuff from both parents. It's exactly why sex evolved in nature in the first place, right? No organism is perfect. It does some things better than others. It would be great if crossover can combine the best of both worlds in a child organism, or in our case, a child neural network. Okay. We have these 2 neural networks. They're embedded in the 2D plane. Give me a straight line that will cut through both neural networks and give us perfect A and B on the left side and perfect C on the right side, so we can bring these together. Okay, that setup should have been pretty obvious, right? There is no such way of doing it. You, obviously, given this setup, can see, well, we take all of this stuff and combine it with all of this stuff, but evolution can't see that. It's going to have a hard time doing that. Imagine that we just tell evolution exactly that it can place a straight line and cut, for example, between the first and the second hidden neuron in both networks. If we do, then we're going to get A from this parent, and we're going to get, which lies to the left of this cut point in parent 1, and we're going to get B and A on the right-hand side of this cut in parent 2, giving us a child that has A and B and A from parent 2. What's the problem with this child? It's missing C, right? So it's missing something necessary. It dies. The second child, with the same 2 cut points, it inherits the C from over here, the left-hand side of the cut point, and the cut point over here. It inherits B and C from parent 1, giving C, B, C, and it's missing A, right? There's no good way we can cut this and combine A, B, and C, the right A, B, and C from both parents. You could imagine a very curvy line that we could maybe wend around both neural networks that would do so, but it's going to be very difficult for evolution to find that wavy line. Yes?
The assumption here is that these are individually the right A, B, and C's, but it might be the case that they are right just together, and once we come up with a new combination, it might be more right than the A, B, and C.
Exactly. So I've greatly simplified this example, right? I'm assuming that A is right regardless of what B and C is doing in a given network, and vice versa. And usually that's not the case in practice, but in this simple case, assume that it is. Okay, so it's going to be very difficult for us if we add crossover to our evolutionary algorithm. If we allow evolution to cut these neural networks in different ways, 99.999% of the ways that evolution could possibly cut these two neural networks in half are going to fail to glue together the right parts. Wouldn't it be great, instead, if we could allow evolution to see inside the neural network and actually see not so much the structure, but the function? That neural network, that evolution could quote unquote see that that hidden neuron 1 in this neural network does more or less the same thing as hidden neuron 3 in this other neural network. Sex and nature obviously lines up DNA and is able to line up genes that code for the same kinds of things by aligning strands of DNA in just the right way. It's actually quite a bit of complicated machinery that goes into allowing Mother Nature to look at two genomes, two sets of DNA, and line them up when recombination is occurring. It's kind of a complicated business. How do we do this for evolution? Back in the early 2000s, Stanley and Michelainen introduced the NEAT algorithm. This is a particular kind of evolutionary algorithm that allows evolution to line up different parts of a neural network, to line up different parts of neural networks that compute similar functions. And I'm going to walk you through how this works. The investigators were pretty clever here. They named their algorithm NEAT, and indeed it is pretty neat how it works. NEAT stands for neuroevolution, so we're evolving neural networks of augmenting topologies. So topology is the structure of the neural network, or the architecture, and we're going to augment it. As we go through this algorithm, we're going to see that NEAT allows us not just to cross different neural networks, but to cross neural networks that have different topologies or different architectures. Okay. In the NEAT algorithm, we are going to cut and combine parts of neural networks very carefully, and I'll show you how this works. Remember that in all evolutionary algorithms, we have a genotype and a phenotype. The genotype is the blueprint that describes the phenotype. The genotype is the thing that mutation and crossover, in this case, acts upon. This is the DNA. And the phenotype is the thing that the blueprint produces, which in the case of NEAT is not a robot, it's just a neural network. The genome, or the genotype, of any one neural network is made up of two lists. The first is a list of neurons, and the second is a list, or nodes, and the second is a list of synapses, or connections. You'll notice here in this example here, this neural network has 3 sensor neurons, 1 hidden neuron, and 1 output neuron. Here's the 3 sensor neurons, 1 hidden neuron, and 1 output neuron. Let's look at the list of synapses. Each element in the synapse list, as you would expect, encodes just 1 synapse. Each element has 5 numbers associated with it. The first 2 are integers, indicating which is the source neuron and which is the target neuron of that particular synapse. The weight of that synapse, as you can imagine, that's pretty straightforward. A binary flag, which is enabled or disabled. So you'll notice that in this example here, this particular synapse that connects neuron 2 to neuron 5 is disabled. It's in the genome, but it is not expressed in the phenotype. This is actually a common phenomenon in biological systems. There are a lot of structures or a lot of genes in our genotype that seem to be silent. They don't code for any functioning subsystem in our bodies. That alone is an interesting topic. We're going to step over that for today and just focus on this competing conventions problem. So we have 5 enabled synapses, and if you have a look down here, you'll see there are 5 edges down here. One of these edges is recurrent. Everything looks pretty familiar up until this point. However, there is this additional 5th value called the innovation value. What this innovation counter does, it's a historical marking. So here's how this historical marking works. We're going to keep in our evolutionary algorithm a global counter. And during evolution, anytime in any neural network that we add a new neuron or a new synapse, we take the current value of this global counter, which is an integer, take that value and assign it to that synapse or neuron, and update that global counter. All right, so we're tagging all of the elements of these neural networks with this historical marking. Even though whenever we tag a synapse, we update the global counter by 1, after a while in evolution, if you look across a population, you'll see multiple neural networks that have the same historical marking value. They have the same innovation value inside them. How is that possible? So we take a neural network, it produces a child. Let's just do mutation for a moment. We produce a child, and a mutation adds a synapse between a pair of neurons. We tag it with the value 7, because that's the current value of the global counter. We increase the global counter to 8. We continue evolution, and a few generations later, we scan down the current population of neural networks, and we see that value 7 in more than one neural network. How is that possible? Why does that happen?
That individual had a high enough fitness value where that was carried through.
It was carried through, right? So whatever that child was that we introduced that value of 7 to, at that point during evolution, it was the only neural network with that value of 7. But presumably its fitness value was high enough that it produced children, and those children inherited that historical marker. So we could, if we looked across the population, we might see 5 neural networks, and in each of those 5 neural networks, there is one synapse that has a 7 innovation value associated with it. That 7 indicates that that synapse in each of those 5 neural networks is descended from a particular synapse in an ancestral neural network. The first neural network that grabbed that value of the counter. Some of you may see where this is going. Why did they introduce this innovation value? And how does it help with the competing conventions problem? Todd?
Well, instead of the hidden neurons being identified by their order, they're identified by key.
Exactly. So it doesn't matter, as you can see in this cartoon, obviously it doesn't matter the order of a hidden neuron. If you go back and look at the XOR functions we were making at the beginning of the course, it doesn't matter whether you create the AND function in the left-hand hidden neuron or in the right-hand hidden neuron, as long as you combine them in the right way. Position in a neural network doesn't matter. The only thing that matters is function. What are these particular hidden neurons doing? But it's hard to identify common function in different neural networks. How do you know that A over here, or how do you know that hidden neuron 1 is doing something similar to hidden neuron 3 in this other neural network? How does this innovation number in the NEAT algorithm help us? How does it help evolution with this problem?
You only need one copy of that innovation in your new child, so you can pick it from one parent or the other, but not both.
Exactly. So if you have these 5 neural networks, each of them has a synapse with the 7 innovation number associated with them, you can assume that that synapse is helping to compute a similar function in each of those 5 neural networks, because they derive from one synapse in the ancestor that was obviously doing just one function, helping with one subfunction, because it was only one synapse at the time. So the assumption underlying the NEAT algorithm is that if you look at different neural networks and you identify that different parts of those neural networks have a common ancestor, as long as that common ancestor is not too far back, those 2 parts of the neural network are kind of doing the same thing. Right? So current Macs and current PCs have a common ancestor way back in the 60s and 70s, the early days, very early days of personal computers. Both Macs and PCs have a CPU. They're different now, different from each other and also different from the ancestor, but not that different, right? They have a common ancestral CPU, which were the first CPUs created for PCs, and then obviously they've diverged in different companies and do things in slightly different ways. Right? We could look inside the DNA of all of us in this room and identify different parts of our DNA that could be traced back to a common ancestor millions of years ago. Right? And those different parts of our DNA, which might actually be in slightly different places within our respective genomes, are doing the same thing. Position doesn't matter, only function matters. And inferring similar function, a proxy for that, or a good stand-in, is identifying common ancestry. So far, so good? Okay, so as in the example here, we want to make sure that in the children we produce one and only one version of A. So as Scott was mentioning here, when we perform crossover, I'll just skip ahead here for a moment. When we perform crossover, we're going to line up the two lists from the two parent genomes according to their innovation number. So I'm just going to look at the synapse lists here. We're going to just ignore the neuron lists for a moment, but it's basically the same thing. So in parent 1, as you can see here, we have 4 enabled synapses, 1, 2, 3, 4. In parent 2, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 enabled synapses. You can see that these neural networks obviously have very different structure. But at the top of each of these lists, we're listing the innovation number. So the first synapse in parent 1 has an innovation value of 1. And the first synapse in parent 2 also has an innovation value of 1. So we take those two elements in the list, and because they have the same innovation value, we line them up vertically. We go to the second element in both lists, and both of these have an innovation number of 2, so we line them up vertically as well. We come to innovation value 3, and we see that there is only one synapse in parent 2 that has an innovation value of 3, no innovation value of 3 in parent 1, so we leave that synapse on its own. Whatever this synapse is helping to compute, it doesn't seem to have any counterpart in the other parent. These two synapses in the two parents have the same innovation number, line them up. This innovation number only appears in parent 1, but not parent 2. Leave it on its own, line them up. And synapses with innovation numbers 7 and 8 only appear in parent 2. Okay, so we've taken these two neural networks and we've taken their list representations and lined up the elements of the list so that now we can perform crossover no problem. We're going to walk from left to right along this data structure, and as we go, we're only going to pick one element at each horizontal position as we go. We start here, flip a coin. Heads, we take the synapse from parent 1. Tails, we take the element from parent 2. In this case, it came up tails. We took the element from parent 2. We visit the second element in the list, flip a coin again. In this case, it came up heads. We take the element from parent 1. Here, there's only one option, so we take the synapse from parent 2, flip a coin. Here, there's only one option. We take the synapse from parent 1, flip a coin, and include synapse 7 and 8 in the child. And if you then take this list and construct the neural network from it, that's the child neural network we get from combining these two neural networks. So far, so good? Yes?
Won't the neural network always keep on increasing in size and hence collapse eventually?
Exactly. So as I just mentioned, whenever we get to a disjoint gene, one in which there's only one instance in one parent and not in the other, if we always combine synapses into the child is going to have more and more, is going to have more synapses than the parents. And if we continue this through the evolutionary process, we're going to get bigger and bigger neural networks, and we're going to be more and more in danger of overfitting. The neat algorithm has several ideas built into it. The first one is this innovation number concept. The second idea they built into it was to start with very small neural networks, start simple, and just let the neural networks get bigger and bigger over time. Sometimes it works, sometimes you get overfit neural networks. This is an old idea. It's been around for 18 years now. There's many, many variations on the NEAT algorithm. Some of them attempt to deal with this bloat issue. We're not going to talk about that today, though. Okay, you'll notice if you look at the structure of the child neural network, the structure looks similar to both parents, but again is also notably different. If you've ever worked with neural networks, for most of us this makes us very nervous. You see a child that looks very different from the two parents. There is no way that that thing is going to compute the same functions as the two parents. This looks like half a PC and half a Mac glued together. It seems impossible that it would actually work, let alone do better than either parents. The brilliance of the NEAT algorithm is that if you try this, more often than not, you get a child that not only does well, but does better than either parent alone, which means the NEAT algorithm is able to successfully take better performing subfunctions from both parents and combine them into a child neural network. We'll leave things there for today. You have a quiz due tonight. Have a good spring break. Assignment 8 is due the Monday you get back from break. Weekly report number 3 is due for the grad students when you get back from break. See you in a little over a week's time.